Yeah, well, welcome to the session. We're going to have four presentations today in the session. The first one is going to be by Bernie. Is that right? Bernie Jenny, and he is from Australia, Monash University, but I noticed it's really an international project with people from USA and from a few other countries, Russia, Switzerland, and so forth. And he's going to present a topic on neural networks for generalized relief shading, contour lines, and coastlines. Welcome, Jenny.
Thank you. Okay. So, yes, thank you very much. I'm going to talk about generalizing relief shading, contour lines, and coastlines. And so these three projects have been a collaborative effort by Dilbert Singh and Bridget Walker of Monash University, Tom Patterson of the US National Park Service, Magnus Heinzler, Mariana Farmakis, and Lorenz Hurny of ETH Zurich, and Timofey Samsonov of Lomonosov State University in Moscow. I would like to start by thanking the Cartography and Geographic Information Society for funding one of these projects with a Rising grant, and the National Geographic Society for funding another project with a Explorer grant. So apparently coastlines, contour lines, and shaded relief, the generalization of those three elements are quite different, but actually what we do is we use machine learning for all three problems, and we use neural networks, or more particularly UNets, for these generalization operations. So we do, and UNets, what they do is they transform raster to raster. So the raster, this can be images, this can be elevation models, or just any other raster as input and also as output. So this is one example, a typical example of how a UNet looks like. On the top left, we have the input. In this particular case, we have an elevation model as an input raster. And on the top right, we have a shaded relief raster again. So this particular UNet converts a elevation model into a shaded relief. And there is a contracting path. This is on the left side going downwards, and an expanding path then going up to the right side again. So the contracting path extracts information from the input raster, and the expanding path then generates a new raster. And when you design this UNets, and we are using this type of UNet for all three problems, so coastlines, contour lines, and shaded relief. When you design these UNets, you have to choose the number of layers. In this case here, we have 4 or 5 layers. You have to choose the matrix size and dimensions and various other parameters, but the general architecture is always the same. And I'm not going into further details about the exact parameters. I don't want to bore you with this. You can find more information in our publications on that. And by the way, why this is called UNet is obvious when you look at this diagram here. It's this U shape that gives the name to these types of neural networks. So in all three applications, the input is a detailed raster and the output is a generalized raster. And so when you create a neural network, you have to train the neural network. And for training the neural network, we use, in all three applications, we use manual reference raster images. So we use a generalized shaded relief, we use generalized contour lines, and we use generalized coastlines in these three applications. So I'm going to start with coastlines. For coastlines, we are using the global surface water dataset. So this is a global dataset, fairly detailed at 30 meters resolution, that encodes water occurrence in between the period of 1984 to 2021. So a white pixel here indicates that this particular pixel was covered during the entire time by water, and a black pixel here would indicate that this pixel was never actually covered by water during this time. And so this is a free product. It has been compiled from millions of Landsat images, and it is very detailed. As you can see, and this is northeast Canada, by the way. I can zoom in and you can see really very tiny details here. So what we would like to achieve with our neural network is transform this raster dataset into this raster dataset. So this is Natural Earth, a new version of Natural Earth that Tom Patterson, one of our project partners, created. So he used global surface water and other sources to delineate the coastline here. He did this manually in Illustrator in a long process. So we are using, we are training our neural network using this global surface water dataset and Tom's Natural Earth dataset. So to simplify the training a little bit, we first apply a flood fill algorithm to remove inland water bodies. That's not related to the neural network. It's a pre-processing step, which is fairly standard and simple to do. So in this little exercise or example that I'm showing you here, we have been using two areas, northeast Canada and this well-known area on the top right, both at the 40-meter resolution. So we use these two areas for training our neural network. And so once the neural network is trained, we can then apply it to other areas, such as the Aegean Sea here. Here is a more detailed view. So on the left side, we have the input global surface water dataset. So that's the detailed input. At the center, we have the output, which is the output of our neural network. And on the right side, we have the Natural Earth dataset that we use in this case as a reference dataset to verify, to visually evaluate our results. And you can see that the neural network successfully removed a lot of small details, simplified the coastline. If we zoom in here on an area, we can see that it actually removed and cleaned this up quite successfully. In the next step, then what we do is we apply a tracing or a vectorizing algorithm to convert this black and white or grayscale image into two vector lines. So this is work in progress. We are currently looking at applying now this or training neural networks with more data, and then also applying this to other scales such that we can vary the level of generalization. So this was for coastlines. Now I'd like to talk about contour lines. So for contour lines, we would like to create maps like this one here. So this is a map of the Swiss World Atlas. It is fairly generalized. It's a map at 1 to 15 million. It has contours at 0, 100, 200, 500,000, 2,000, and 4,000 meters elevation. And you can see it's really very generalized. So what we would like to achieve is, or create, is a neural network that takes a detailed elevation model, creates a generalized elevation model that we can then use to, in a contouring algorithm, to create contours like this and then fill them with color. But we have a problem because contour lines obviously are lines and not raster. So what we do in a pre-processing step here is we use the manual contour lines of the Swiss World Atlas and use ANUDEM, which is a classical and well-established algorithm for converting contour lines into elevation models. And we create a series of elevation models that we then use for training our network. So we did this here. These are a few patches of our ANUDEM output. So these were created from the manual contour lines using ANUDEM. When we put them together, that's the central European, Alpine, Northern Italy area that we use for this exercise or this demo here. So we use this elevation model created from the contour lines, and we use the EUDEM elevation model for training the neural network. So EUDEM is a fairly detailed elevation model. So we train the network, and once this network is trained, we can then apply it to other areas of using the EUDEM or other elevation models. We create a generalized elevation model, and then we apply an algorithm, a contouring algorithm, and fill the contours with color. So this creates these images here, or these output. On the left side, we have the high resolution input elevation model. On the right side, we have our contour lines created with our neural network. This is Sicily. This is part of Norway with a very complex coastline here. Again, on the left side, the detailed input. On the right side, the output of the neural network with a contouring algorithm. And this is another comparison here is Scotland. And finally, here, this is Corsica. On the left, again, the high resolution input. At the center, the output of the neural network. And on the right side, we see, again, so we use the manually produced contour lines as a reference to evaluate our results. And you can see our neural network currently, or the version that we created here in this experiment, misses the highest peaks. The highest peaks here have been emphasized by the cartographer when they created the contour lines manually. So we are working on improving that. So let me move on to shaded relief. So for shaded relief, we would like to create something like this. This is a manually created shaded relief. It's almost a piece of art. When you create a digital elevation model, you would usually assume a top left illumination. But the cartographers, when they do this manually, they vary the direction of illumination locally to emphasize large landforms and to emphasize important smaller details. And they do this throughout the area or the shading. They also emphasize illuminated slopes. So they identify large landforms and brighten up the illuminated slopes and do the opposite for the dark slopes. So darken the dark slope, the shaded slopes. So that's what we want our network to do. And so we are using shaded reliefs that were created manually by Swiss Topo for their national map series. In this case here, we use about 70 plus sheets of the 1 to 50K map series. And so this resulted in Edward. And Edward is an app that now includes those neural networks. We have included 3 different neural networks in Edward. This is the detailed one. So the one trained with 1 to 50K shadings. You can see it's fairly detailed. We have a medium scale one trained with 1 to 200K shading. You can see the large landforms here are emphasized. And then we have a small scale shading trained with 1 to 500K. And you can see there's quite a bit of generalization applied to this one. So this is a comparison here, detailed, medium scale, small scale, and the same area shaded with a standard digital algorithm. We can also adjust the direction of illumination. Usually we'd use a top left illumination, and I'm using a bottom left, bottom illumination, which can lead to a relief inversion, as we know. But I want to emphasize that the network actually learned to adjust the direction of illumination locally to emphasize the large landforms and also smaller details here. We can do another type of generalization, which is a macro generalization, which emphasizes the large landforms. This is a generalization that we applied to the elevation model before we shaded. When we apply this quite a bit, as in this example, you can see that it gets a bit noisy and grainy. In this case, we can also do some minor filters and remove a few details. So micro generalization here. So the level of generalization, of course, will depend on the map scale and your map purpose. Aerial perspective is something else that we can apply. I'm running out of time here, so I'm going to skip this. And then there's also the possibility to emphasize details in flat areas, as in this example here. So I'd like to invite you to have a look at our website, edward.earth, if you're interested in this. And Edward is available on the Mac App Store. And I think that's my last slide. I don't know whether we have time for questions.
Thank you. Thank you. That's great. Yeah, we have time for questions. Yes, you have. You can use this.
Yeah, thank you for your presentation. I really like this software, and I have a specific question related to when you the parameters when you change in the software. So, how did you realize that when like you pre-trained a lot of different models based on different parameters, or there is some other result solutions that you can change the parameter?
So we have 3 different models for the three different styles or scales that I showed. And the other parameters, actually, they are applied to the digital elevation model before we shade before we create the shading with the neural networks. So they either emphasize details in flat areas or emphasize the large landforms, etc. In the elevation model, and then we feed that modified elevation model into the network.
Okay, thank you.
Any other questions? Thank you. More questions? Dabian, could you also check online to see if we have questions from the virtual participants? No. All right. Well, if no more questions, thank you, Bernie.